how to implement some of these theoretical ideas.
Okay, yes, thank you very much for thank you very much for the organizers for inviting me. I've never been in Oxford before, and I'm happy that there's such beautiful weather. I'm really able to enjoy that. So what I'm giving you today as an overview is a bit of information about how the status is in trapped ion quantum information processing, which types of experiments we are able to do in Innsbruck. And yes, basically a bit of the snowy mountains. Not like that anymore at the moment, but so here are 4 different directions that we are currently pursuing in Innsbruck. One direction is going towards quantum network, that is quantum interface. There's a cavity around and trapped ion inside such an ion trap. And what we're doing there is really generating, for example, entanglement between the photons and the ions inside the trap. So that is going in direction of the quantum networks. One different approach is then going towards scalability of the system. That is, we are designing surface traps to scale the systems to a larger number of ions. Currently, we are doing all the really quantum information processing experiments in such a microscopic ion trap where really these plates are a millimeter apart, and where, well, this is really made in a mechanical workshop and not really micro-machined by etching techniques and things like that. So we want to go to much more ions using such ion traps. Then also there's, of course, directions using such trapped ions for precision metrology. So building atomic clocks, very, very precise atomic clocks. But I'm also not going to talk about that. What I'm actually going to talk about is rather the implementation of algorithms in such systems, like, for example, error correction and simulating open quantum systems. Okay, so the outline of my talk is basically first an introduction of trapped ion quantum information processing, how it works, how we manipulate these ions, how we do actually the quantum gates. And then I will explain on 2 examples, one at least, let's see how far I will actually get, on the repeated quantum error correction, and maybe also a bit on open system quantum. Good, the system that we are using is, as I said, such a macroscopic ion trap, where really the plates are machined in a mechanical workshop. We trap these ions here inside such an ion trap by electrical fields, oscillating electrical fields in that case. I don't want to go too much in details how that works. Just the ions are trapped, of course, all of them are charged and they repel each other. Due to that, of course, they are trapped at a distance, and the distance between these ions is on the order of 4 to 5 micrometers. So here you see a picture, a fluorescence picture of these ions. And each of these points, there is of course one single ion, and you can address them then by lasers. Also individually manipulate them and do quantum operations on them. The atoms that we are using in Innsbruck is calcium-40 plus ions. The advantage of these ions is that they have a stable, very, very stable state, D-state. It's a metastable state due to the fact that there's actually no p state lower than that, and due to that there's no decay process that is directly going down, but you have rather a quadrupole transition or some offers and two-photon transition that is going down. And due to that, the D state has a lifetime of approximately 1 second. So the qubit that is stored now in these 2 states, for example here the 0 state and the 1 state that we use as qubits, lives due to the lifetime of the excited state approximately 1 second. In our case, it lives a bit less than that due to other technical imperfections on the order of 100 milliseconds. Now we can manipulate these qubits by using this 729 nanometer laser. It's a very, very narrowband laser. It has a line width of 2 to 3 hertz, and due to that, it's more or less on the same order of magnitude, the line width, as actually the line width. Then we also use this P1/2 state to actually detect the ion state. What we do is just shining in another laser on this transition, and of course the 1 state will now see this laser, it will scatter photons, and due to that the ion will burst. Whereas if the ion is in the D state up here, it just doesn't see this laser, it's not excited by that, and it's just staying. So by just scattering this laser light, we know was it in state 1 or was it in state 2. So how do we now do quantum operations? So what you have, of course, is then this circuit model, and of course you want to do, for example, C0 gates, individual qubit rotations and things like that, and we have to somehow do these qubit manipulations. So, for example, single qubit manipulations, what we do there is just that we shine in this laser on this transition, onto an individual ion, for example, and we just wait for some time, and for example, if it now starts in the S state down here, and we just wait for some time, it will oscillate in between the ground state and the excited state, and if we then switch off the light, of course it will stop. So we can generate an arbitrary superposition also of this S state and the D state just by shining in this light for a certain moment. So it's just a rotation, of course, on the Bloch sphere, and actually the rotation axis, whether it's rotated around X or whether it's rotated around Y, can be controlled by the phase of this laser. So by that you can do arbitrary rotations of this laser. Okay, how do we do the entanglement operations? For that we use the motion of these ions inside the trap. For example, here the ions are oscillating all in the center of mass mode inside this trap. Of course, it's much more than we actually use. It's really macroscopic oscillation, whereas we use really the quantum oscillations, the phonons. And this quantum oscillation then can be used to exchange information between these.
And sorry, is this picture real or simulated?
This is a real picture, but of course you really oscillate by changing the electric potential. So you really displace this harmonic oscillator very, very much, and then decide to shake it in resonance with this oscillator. I think it was actually done something like 10 or 12 years ago, but it's just
it's like an icon now, I think, right?
Okay. So we have now this qubit, that's the qubit of the ions, the S state and D state. We can manipulate them by the laser. And of course we have also now the harmonic oscillator of this ion motion. And we can use now these 2 degrees of freedom to do qubit manipulations. And for example now, this is of course a product state of these 2 degrees of freedom. And you can now use lasers to manipulate that. You can, for example, with a Blue detuned laser, that's Blue detuned by one of these oscillation frequencies of these phonons, you can actually generate a phonon at the same time as flipping the ion, or you can actually take it out by such a red detune. And you can actually see that also spectroscopically. For example, scanning your laser now, you can see this is the carrier signal that you really drive the ground state to the excited state directly on resonance. And you can also drive now the center of mass mode by just detuning it by one frequency. So there's, of course, the blue mode and the red mode as a function. Okay. Actually, in our experiments, it's slightly more complicated because we have now different laser beams, and we also want to manipulate now these ions in a very specific way, and of course we want to have fidelities as high as possible. And the manipulation that I've shown you so far actually doesn't give you the perfect fidelities of your operations, but we have to have now a set of operations that has quite high fidelity of larger than 99%, and I will now just explain you what these operations are. So there's 2 lasers. There's a global laser exciting all of these ions at the same time, and there's one laser that's actually individually addressing these ions. The waist of this beam is on the order of 2 micron. With a distance of 4 micron, then this beam is already decreasing fast enough that you don't manipulate so much the neighboring ion anymore. Of course, there's still some error due to that, but in first order that can be. Good. So what we have is now this global beam. The global beam is now exciting all of these ions at the same time, and we just go on resonance to this transition. Of course, what will happen then is that all of these ions will rotate around the Bloch sphere at the same time. For example, all of them around the x-axis, or all of them around the y-axis. But it's just a rotation of all qubits at the same time. So there's no interaction between these ions involved because they cannot talk via this motion. Then there's also a possibility now with this address beam from the side that we actually make it just very strong and detune it. What happens then is that you have an AC Stark effect that shifts these energy levels, and due to this shift, actually the clock, the ion is actually operating more or less like a clock. It's rotating, it's in the rotating frame, it's rotating, and now with respect to the laser that you usually manipulated, it's either rotating faster or slower. And due to that, you actually have an effective rotation of your Bloch sphere around the center. And you can do that now individually for each of these ions. And together with these global operations of x and y, you have now arbitrary single-qubit rotations. Of course, it's a bit more complicated. You have to do a sequence of different passes, but you can manipulate each of these ions individually arbitrarily. Okay, and then you have also an entanglement operation, and for the entanglement operation we also use this global beam that manipulates now all of these ions at the same time. It's a so-called Mermer-Sørensen entanglement operation. What it actually does, I will explain you in a minute, but you can actually look at it as something like such a super Bloch sphere. So you have both ions, for example, in the ground state, or both ions in the excited state, and you actually rotate in this super Bloch sphere so that you can actually generate also, for example, an SS plus DD state is an entangled state. So what happens there is that they exchange phonons and flip at the same time. The fidelity of such an operation for 2 qubits is above 99%, for 3 qubits 97% or something like that. And it drops, of course, with the number of ions, but fidelity, at least for 3 qubits, is still low. Okay, and then together with the qubit rotations, you actually have an arbitrary, a full set of unitary operations so that you can do arbitrary unitary operations. Okay, then we actually extended in the last year also this tool set with one additional operation, and that is actually non-unitary operation. Because sometimes, for example, for error correction, for resetting qubits, you actually need a non-unitary operation, for example, resetting the qubits to initial state. So that's also an essential tool that you need for quantum information processing. And the way we do this resetting is that we have this qubit here in the 0 and the 1 state, and there's actually additional Zeeman levels there, and we use these additional Zeeman levels now to reset this qubit. What we do is that we just start from the 0 state, we make a pi pulse to this state, so all the population from here will be transferred down there. And then we just use optical pumping. So we just send in a sigma light going here to the P state, and with spontaneous decay it will end up. So all the population that was up here will be pumped down here by optical pumping, and all the population down here will stay. It's not affected. So it's really a reset, and we can use that, for example, also to couple our ions now to the environment, because the spontaneously emitted photon can actually take away the information, what qubit you had. And if you trace over the environment, over these photons that were scattered, you actually control the coupling to the environment. Okay, and as I said before, readout is done by this fluorescence detection in the end. We just scatter photons on this transition. And here, for example, you see 2 ions. And here, both of them were in the bright state, in this S state down here. Here only the left one was in bright state, or the right one was in bright state, or both of them were. So in that sense, you can really detect it, and you can detect it with above 99% fidelity. So it's really, really high efficiency that you detect these things. Okay, so the state of the art, that's what we are able to do with that, is that we are working usually for full quantum control with something like 3 to 5 ion qubits. And what we'll also show you in a minute is the entanglement of up to 14 ion qubits. That's what we can do using this Mermer-Sørensen entanglement operation, up to 14 qubits. I don't know whether anyone at the moment is a bit above that. I guess sooner or later someone will. Gate fidelities for 2 qubits is currently above 99% fidelity, and for the operations, the laser passes that we use, we're using up to, let's say, 100 sequence of 100. And sometimes now we are even limited by our experimental control, and we have to probably put a bit more effort in that. Okay, that's how it looks like in real life. It's the vacuum chamber. The ion trap is inside here. You have down here an oven that you just generate a flux of atoms going through this ion trap. And then from the side you actually rip off the outermost electron and the ions stay trapped inside this ion trap, and then you can work. This is how it looks like actually in reality. There's a big magnetic shield around so that all the magnetic fields from outside don't affect. So it's a 1 by 1 by 1 meter cube. It's quite a big system. Good. Generation of QISW states, so the entanglement of up to 49s. I don't want to go too much in detail here. So the way it works is that you start, for example, in the SS state, and now you flip both of these ions, first the first one, and then the second one, and they actually exchange one phonon. So first the first one flips, puts one phonon, for example, in, and then the second one flips and takes this phonon out. So they actually exchange this phonon. What you have to do for that is that you have two colored laser beam for that, one blue tuned, one red tuned, so that the first one puts the phonon in, and the second one takes this phonon out. And if you do that in a very controlled way, then you can actually start with this SS state and generate after some time this SS plus DB state. So it's of course an interference of all these different paths here that can happen. And this nice thing about this Mermer-Sørensen gate is that it actually doesn't matter in which quantum number of the motion you start, the coupling between these two states is independent. Due to that, we are not actually affected by the thermal excitation of our motion. Even for quite high numbers of motion, we can do these operations with high fidelity. Of course, for 4 ions, that gets much, much more complicated. For example, here you have all these different paths, and you get actually a quantum interference of all these different paths. It's like a big interferometer. And of course, after some time, you also here generate this position of SSSS plus DDD. So you get a destructive interference of all these intermediate states, and they're not populated. You know, I guess you can also imagine how big this interferometer gets for 40 minutes. Okay, that's how we detect the entanglement in the end. I also don't want to go so much into detail here. It's the so-called Parity Oscillations. You can think about it again like a big interferometer, where you actually have either SSSS, so either they go one way, or all of these atoms go one way, or all these photons go, in a photon picture, all of these photons either go one way, or they all go in another way. And then actually changing the path of one of these arms actually affects the system in such a way that you get fringes that are n times the phase. So it's n times more sensitive, such as a QISW state, changing the phase of the second laser than a sigma. That's what we also observe here. So for one atom, you get actually an interference fringe, the parity oscillation fringe, that actually oscillates within 2 pi bonds. For 3 ions, for 2 ions twice, for 3 ions 3 times, and so on, for 6 ions 6 times. And here you see the fidelity that we derive from that. For 6 ions, it's still around 90%. Fidelity of this entangled state, the QISW state. For 14 ions, it's just still a bit above 50%, which means with some precision. So it can be that it's not entangled anymore, because the below 50% is actually not really entangled anymore. But we are still above of that, and due to that, we are very, very sure that, just to say that we actually have.
And with 12 ions, you get that you're not entangled?
Yeah, we probably had some more technical problems there. Okay. So it's really adjustment. You really have to adjust it quite a lot to really get this. And it has to be stable for quite some time to really measure things. So it might drift a bit away, and if you don't adjust it very well, then you might not be able to get it. So it's really just technical. Okay, going to the experimental repetitive quantum error correction. Here's a schematic of that. The main PhD student who was doing that is Philipp Schilter, together with all the other PhD students. Julio Barrero was the postdoc on that project. And we had help by Volkmar Nebendahl, who actually helped us to derive the pulse sequence. I will also explain you in a minute how that works, how to actually get such a pulse sequence. And it's not so trivial because the gates are quite complicated. Okay, so the main thing that we did there was just a standard repetition code. It's just 3 qubits, so it's not probably very, very useful for quantum error correction, because such a code can, for example, only correct for a bit flip or a phase flip, but not for both. Okay, so encoding is, of course, you start with normal qubit, alpha 0 plus beta 1, and then you distribute this information over 3 qubits, 2 auxiliary qubits, so that you still get to the alpha 000 plus beta 111. And now in this state, actually what can happen is that one of these qubits flips. Either, for example, the third one, second one, first one. And of course, all of these states are different, but in principle you still have the information there. There's still alpha and beta there. And using now the majority vote, so to say, you can actually also say which one has flipped without destroying the information. So you just do this 2 CNOT operations that actually gives you then on these 2 qubits the information which of these ions has flipped. For example, if the first one has flipped, then doing these 2 CNOT operations will result in 1-1 in the 2 auxiliary qubits. And this information 1-1 tells you now first ion has flipped. It's not entangled anymore with the first ion after these 2 CNOT operations. And the 1-1 now tells you, okay, flip the first ion back. And that's exactly what this Toffoli operation does. If this one is 1 and this one is 1, then it flips the first ion. So that's the standard repetition code with the quantum feedback. Usually people before had just measured these 2 states and corrected it by a qubit rotation, controlled qubit rotation. But you can also do it with the Toffoli operation.
But this quantum feedback doesn't only work if you fix the basis in which the error may occur. Otherwise you have the problem that you can't get rid of the entropy. I mean, there's no general error correcting code where you do everything unitarily, you have to measure at some point.
Yeah. I mean,
yes,
if you reset it afterwards, then of course the entropy is taken back.
Yeah, exactly.
Okay. So in that sense, you also somehow have to erase the information, of course. Either you take fresh auxiliary qubits,
yes,
or you have to reset them afterwards to take them. Otherwise it doesn't work. Otherwise it's just a unitary operation, and of course with the unitary operations you cannot do it. That's correct. Okay, so of course this, what I told you now, is just correcting for bit flip errors. In principle you can modify that to correct for phase flip errors. The thing is just, for example, this is a bit flip, so the z-axis is just flipped. A phase flip would be, for example, here, a flip in the equation plane. And it's actually exactly the same, just a different basis. So our main source of errors is actually dephasing and not bit flips. Bit flips, for example, you would have to some extent when you have the spontaneous emission. It's a bit more complicated, spontaneous emission, than just bit flip. But what we mainly have is dephasing, and dephasing comes in our case from magnetic field fluctuations or from laser frequency fluctuations. So it's basically the rotation of our Bloch sphere. The atoms are one clock, the lasers another clock, and if they go out of phase, then we have phase errors. And of course, magnetic field fluctuations, since the ions are very, very close together, and laser frequency fluctuations also, since it's one laser that is affecting all of these ions at the same time, they will affect all of these ions equally. So you will have just the 2 clocks running, not in the same frequency, so to say, and due to that we have phase errors for all of these ions in the same direction. So it's actually a kind of collective phase error for all of the ions at the same time. We'll come to that in a second again. So we want to correct for such phase flip errors, and due to that, of course, we also need to change our basis now. So before I had told you here about this error correction of the bit flip errors, and to change for phase flip errors, we just need to go from 0 to plus, or from 1 to 1. So it's just a Hadamard operation, before and after your error occurs to actually be able to correct it. Okay, now of course we have the sequence. We can probably put some additional operations here before and after that commute with our errors. And now we want to do such an operation. We want to have our native operations that I told you before, and we want to do these operations. And it's actually not so easy now to know which pulses you actually need to use to do that, because there's no C0. I cannot put here just the C0 operation, because it doesn't really exist with our operations. We have different types of entanglement operations, and we need now to know how pulse sequence. So what we actually do, and that was the work by Volkmar Nebendahl, our theorist there, he wrote a modified grade ascent pulse engineering algorithm. That's an algorithm that actually optimizes our pulse sequences so that the unitary operation that we get in the end is exactly the unitary operation that we want. And of course, so we want to maximize this overlap of this unitary operation. And at the same time, of course, we want to have our pulse sequence as short as possible, because each pulse, each operation induces errors. And if you have less pulses, then all errors will also be bigger. So that's an additional condition that we put in there, and then you just try different operations and by that optimize this pulse sequence. Of course, similar things have been done before in NMR. They also have done similar pulse optimization algorithms. We just adapted them for our sequence. Okay, and doing that from this sequence that we had, we actually get this as a sequence for our operation. So this is just one entanglement operation, one Murman-Sørensen gate. Here's another Murman-Sørensen gate, and these are global rotations, and this is an individual rotation of an individual gate. So these are the operations that I explained to you before. So that's the sequence that we need to do. So you encode now, do the error, decode, and of course to repeat that we have to reset our qubits, as we've discussed before. And the reset of our qubits, I already explained to you before, it's just this optical pumping back into the ghost. That's what you use for these two lines after the sequence, and repeat just the same. Okay, now how to test that our error correction protocol is working. Of course, we can just do the encoding, the decoding, and that's it. No error in between, and we can test how good it works. Then what we can also do is, for example, induce now on one of these qubits phase flip, and test again. Does it work or does it not work? And in principle, since the error correction protocol works, it should give the same outputs later. Of course, then what we also want to do is use this error correction protocol actually for something useful. So for noise, like noise that is affecting all of these ions at the same time. For example, our noise that we have is dephasing. Does it correct for that or not? But as we said before, there's some special dephasing. There's uncorrelated noise and correlated noise for these ions. And we probably also need to distinguish that. So we did that. We started just with a sequence. Just preparing a state and detecting it, we already get 97% fidelity. So already there the fidelity drops slightly. If we do one error correction step without any error yet, fidelity drops by something like 10%. So that's just because each of these gate operations has a fidelity of 99%, and if you have 10 operations, of course it will drop by 10%. You can repeat it again, 2 steps, 3 steps, and each time the fidelity drops by more or less 10%. Okay, now you can also induce the single bit flips as an error. For example, for the first qubit, for the second qubit, you can average over that, and you see the fidelity doesn't drop with respect to applying no error, so that means the error at least is correct. Okay. Now if we do random single qubit errors, of course, it's just each time that we repeat the experiment, the computer decides which error to do, and then in principle it should do exactly the same. It takes a bit longer, and due to that fidelity drops. It drifts a bit further away. Okay, so the quantum error correction protocol principle works. Now let's look at the real dephasing. And the real dephasing in the blob sphere is, of course, something like that. So you have the blob sphere here. And now let's just look at the equator plane. And of course, you have some vector here. It rotates arbitrarily around, and you average over that. So effectively, the vector will actually decrease here. Okay. Now, correlated versus uncorrelated noise. I told you all of these ions are shifting equally, and due to that, you get errors of all of these ions in the same direction. That's correlated noise. Of course, you will get bit flips for two ions much more likely than if the errors occur individually for each of these ions. Okay. So, if each of these ions fluctuates individually, then you would expect some lower errors. How can we do that? I told you correlated noise is actually the intrinsic noise that we have in our system. So for that we just need to wait in between and the error will occur. We have that anyway. Or for this uncorrelated noise, what you can actually do is just a weak measurement. So a weak measurement is actually a bit flip. It's the loss of information of the phase information. Why is that so? For example, let's assume now you have some vector going in some direction. So here's 1, here's 0, and here's just a cut through this blob sphere. And if you now project onto the z direction, what will happen is that this component of your blob vector will just get lost. It will be just projected onto the z direction. So the phase information is completely lost by a measurement. And if you have a probability 1, it's really completely lost. If you have probability 0.2, of course, you just reduce the blob vector in that direction. So such a measurement, of course, affects all of these ions individually. Each of these ions is measured individually, and due to that, you actually get it uncorrelated. Okay. Why is it important? Of course, if you have such a state, encoded state, and now two of these ions flip, the error correction protocol unfortunately doesn't correct for that. It actually corrects just in the opposite direction. Because you make this majority vote, and now two of them are flipped, and it will correct in the wrong direction. And now, measuring now the two-bit error probability, of course, for correlated noise is much bigger than for uncorrelated noise. So, we tried that now. That is the fidelity, just if some error occurs with some probability, the fidelity, of course, will drop. So, no error at all, of course, the fidelity will be perfect. If it's 0.5% probability the qubit flips, of course, fidelity is half. And if it flips with 100%, of course, you know exactly the state again, so it would actually be fidelity equal to 0. But in worst case, it's actually that it flips with 50% probability. Now doing the uncorrelated bit flip error, the phase flip errors, we did that now. Of course, it starts again with 0.9% fidelity. And if you now make this weak measurement with some probability, in some region here you actually surpass this limit of the uncorrected noise. So that means with some probability you have corrected the qubit. Okay. So you have done some error correction and you get better by doing this error correction. Of course, in principle you would like to shift the fidelity here at the beginning much, much higher so that it really helps you. But you can repeat it and it will increase and increase and increase. That's the error threshold. Of course, for correlated noise, you get higher probabilities to have two bit flips, phase flips, and due to that, of course, the error goes down much, much faster, and due to that, you cannot really correct. So our intrinsic noise we cannot correct, but a measurement we can correct. Measurement errors. To some case. Now that there was actually a proposal by one of our referees for the first paper, but that we actually could correct for a full projection of one of the qubits. Just when one of the qubits is measured, the error correction protocol should really still work perfectly. So in principle, you can measure here one of these qubits in between, and after the decoding, you could recover the same qubit. So you can actually do something like a measurement reversal. Of course, in some sense, you have to be careful because the measurement actually doesn't tell you anything about the initial qubits. Otherwise, the state will be destroyed. The reason for that is that you actually measure in a direction that is orthogonal to the information. So that the measurement doesn't distinguish now between plus 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 or minus minus minus. There's no information in this. So it doesn't change the alpha and beta population. Okay, so what you need to do for that is, of course, if you measure here, you shine in your laser, and due to that, these photons will scatter light. Of course, these ones shouldn't scatter light because they will also be projected by light. So what you need to do is to hide these ions from the measurement. What you do for that is just you hide that by hiding this atom in the other D state here, up here. And this other D state is also not affected by this laser. And due to that, the qubit now in this code, 0 and 1, will not scatter light and will not be projected. So that's the hiding operation. Of course, now this ion scatters photons, and if it doesn't scatter photon, it was in D state. If it scatters photons, it was in S state, and by that you can distinguish in which state it is. The problem then is, of course, this measurement also heats up your ion strength. There's a lot of photons being scattered with all other momenta, and it actually scatters these photons. It's a random process, and due to that, your atoms will get quite hot by that. So what you need to do these entanglement operations afterwards is that you need to record this measurement process, and then you can do If you do that, what you will actually get is a fidelity. If it was measured in the state D of 79%, it would be in the same qubit state again. If it was measured in state S of 74%. The reason that this is slightly low is because, of course, you heat it up quite a lot and you need to recool it. This state scatters photons, while this one doesn't scatter photons. Due to that, this one gets much hotter and needs to be recooled. And due to that, you have something like this. Okay. I probably will just shortly go over that. In principle, what we did then in some other experiment was to simulate open systems, open quantum systems. So the reason for that is, of course, you want to simulate quantum systems, for example, magnetism, due to the fact that there's a really exponentially growing Hilbert space, and quantum simulations actually could help you to understand such systems and to do something that probably you cannot do with a classical computer. So for something like that, you want a quantum simulator, and of course we are not the only ones doing that. There's quite a number of other people, for example in NMR, Chris Monroe's group, Tobias Schett's group, was the first one doing it with trapped ions. And of course, there's also now a huge effort to do that with quantum. Okay, what we have is of course a quantum, what we can do is, of course, we can operate our quantum gates. Okay, and this is different to what has been done before. All the others have actually done analog quantum simulation. So they use the Hamilton operator that is similar to the one that they want to simulate. And of course the system should also be very simulated. With a digital quantum simulator you can actually do something a bit more general, because for example with your universal set of gates you can do, for example, this Hamilton operator somehow, and you can do this Hamilton operator somehow. Of course the complete Hamilton operator, H, is H1 plus H2. Can you do that as well? Maybe not so easily. Okay. But what you can do is that you can actually do a Trotter expansion of that. And first do the first pulse, then do the second pulse. So here should be H2, I think. And of course, you do some error, because if you only make small time steps in the first Hamilton operator and the second time operator, there will be some error due to this commutative relation. But if you make the time steps small enough, the error will actually drop quite a bit. And that's what we did also in cooperation with Ikoki. For example, here is an Ising model of two spins. You can simulate this as a magnetic field that just rotates the qubits around Z. And here's an entanglement operation, an XX operation. That's actually just how normal it is. And if you do that, for example, here is the trottering for really big time steps still. You see it doesn't really fit to the theoretical curves. But if you reduce these time steps, it actually follows quite nicely this theoretical curve. So you see that these trautorization errors, you can really suppress them quite a lot by making these time steps smaller. What I actually wanted to show you rather is to simulate, well, probably not so much anymore, that we are able to simulate open system quantum simulations. What you of course need to do there is that you need to control somehow the coupling to the environment, and that's what we were able to do. So coupling to the environment is of course a non-coherent process. So you have to model that with a master equation. You have usually a coherent process and a non-coherent process. And the non-coherent process is usually something like written down there. So you have some jump operators, C and C dagger. And you have to somehow engineer this jump operator to be able to control such an open system. Okay. So the coherent jump operator, for example, for spontaneous emission is something like that. You start in excited state and you map it to the ground state. And this, of course, operating this master equation then gives you just the explanation. In principle, we of course need to do that now digitally, which means we have to do step by step applying these jump operators and by that simulate such an exponential decay. I don't want to go now too much into detail, but for example, this was the optical pumping, for example, from -1/2 to +1/2. You can also now engineer a special type of jump operator that actually affects both of these ions at the same time, for example, doing bell state pumping. So for example, if you were in these two bell states, they are mapped up here, or if you're in these two bell states, they're mapped over here. So in principle, if you start with any arbitrary state, in the end you will end up in this tiny state. Okay. You can engineer that. I don't want to go now too much into detail. We use an additional ancilla qubit, you couple that coherently to these other two qubits that you want to pump into this bell state, and in the end, the information, whether you flip that or not, is on the ancilla qubit, and you need to reset it. We have done that. I don't want to go too much into detail there, but what you see here is, for example, you start in a completely mixed state at the beginning, you pump it, and in the end, you reject it. Relative sensitivity. In principle, if you don't want to now map directly to this bell state, what you need to do then is you need to do these small steps, so small pumping steps. And if you do that, you actually see something similar to an exponential increase of this pumping. Okay, to summarize, I've shown you some examples of such quantum algorithms that we are able to do now, the repetitive quantum error correction, including such a reversal of a quantum measurement, and also some open quantum simulator, which is actually able here to pump into a bell state, starting from an arbitrary initial state, mixed state even, and there's additional things shown in there, for example, pumping to a 4-qubit QISW state, in this case, So now I would like to thank to all the people who contributed to that. Of course, Rainer Blatt and all PhD students and postdocs working on that. Also theory people who were helping us with that. Markus Müller did really a good job in designing these part sequences for the open quantum simulator, of course with the help of Peter Soller. And for the quantum error correction, Volker Nebendahl helped us to get this part sequence. And of course, there's a lot of money also necessary for doing that. Yes, we have great help. Okay, maybe just a short advertisement. Direction for me, myself, how it will go to. I actually want to generate some trap back ions, and I got some money for that, and it's just a project. So, but I don't want to go into detail. Okay, thank you for your attention.
So do we have any questions?
Could you say a bit more about the issues of going, when you go to all 49s and the error? Could you say a bit what gives rise to this error and
So the main problem actually that we have generating this entangled state is that entangled state doesn't live very well. The reason for that is actually that it's more sensitive to these phase errors, and already during the generation we had actually a lot of phase errors. So it's much more sensitive, and due to that the state decoheres actually not with the number of qubits proportional to that, but it actually decays with n squared as a number of atoms, which means having an initial coherence time of these states of something like 10, 20, 30 milliseconds, already with 14 ions in the generation time of something like 50 microseconds, the state decays very quickly. So the GHZ states are certainly not the best states to generate entanglement because they decay. Other issues, yes, I mean, of course, in such a linear ion trap, it's not really easy to have 14 ions inside. In our case, even we already are in slide 6 configuration, but it doesn't matter so much because remember the engagement looks good.
What is the use of optimal control for the pulse sequence? I mean, of course, I know the jargon that it helps a lot and so on, but in principle, one could also just use any universal gate set and just do it. I mean, almost the relationship in overhead and errors you would have by just using a naive universal gate set versus your sophisticated like for an dial type optimal control.
So really, you mean by shaping and frequency and amplitude and everything like that?
It's kind of outside the usual gate set picture.
I think it very much depends on the operations that you actually want to do.
Okay.
That's what I assume. I also don't know how big the overhead is in the end to really calculate the optimal.
Okay. That's another issue.
That's another issue, of course. I'm not 100% sure. We didn't really try it out yet, I must say. The optimum control pulse sequences. We rather tried it out by hand. Okay. Sometimes doing adiabatic passage sequences for doing pulse or something like that. Sometimes they were better, sometimes they were worse. It depends very much on the problem.
What are the major advantages and improvements you expect from using Rydberg atoms or Rydberg ions here?
So in principle, the main advantage that I hope to have there is that actually, if you look at the dipole-dipole interaction that you have, the normal dipole-dipole interaction of the motion, actually the oscillation of your ions there gives you a dipole moment on the order of 300 dBi. So that's the magnitude of your oscillation. Of course, it's a charged particle, and due to that, you get an oscillating dipole moment. On the other hand side, for example, microwave-pressed Rydberg ions would get a much bigger dipole moment, and due to that, of course, the interaction would be also much faster. Because then, I mean, if you have a factor of 30 or something like that, increase in dipole moment, you get a factor of 100 or so. Of course, you're running probably in the other problems because the Rydberg states are of course not very long stable, and then due to the lifetime of these Rydberg states, you might get infidelities, even if they're like very
Not faster.
They could be faster. And I hope also, for example, if they are faster, maybe you can even pull them a bit further apart and still get a sufficient interaction with sufficient entanglement operation. So in that sense, for example, if you have an array of ions or something like that, maybe it's possible even to bridge the gap between two individual charged ions.
So you said the current state of the art is like 14 qubits and can do 100 unitary operations. So is that kind of, I mean that's like the square, right? And when designing algorithms, there's often tricks you can do to trade off between the number of qubits you need and the number of time steps. So what shape algorithms would you prefer? Like, is it like the square? Or is that the kind of relationship for these systems?
I mean, in principle, yes, it's similar to that. So the fidelity, for example, for the entanglement operation, as I said, drop with n squared, the number of ions, which means also the fidelity, the total fidelity is of course often more or less the sum of the individual fidelities of the individual ions, of the individual operations. Okay. Which means, for example, if you reach here 50% fidelity, of course all the information is lost, and you didn't do anything. So if you have 1% infidelity per operation, then you can do something like 50 operations. If you're a better infidelity, you can do more. But now if this fidelity here scales with 1 over n squared, with the infidelity, okay, 1 minus the sum of I, infidelity of each of these operations scales with 1 over n squared. I guess it's more or less also the n squared behavior, the number of lines and the infidelities that you can sum up to. I guess that's more or less it. The reason why we're actually able to do something like 100 operations is that we, in the meantime, sometimes in between, do incoherent operations that actually pump into the state back that we want to be. Otherwise, the fidelity would be lost.
Okay, let's have a cup of tea. Thank Markus again.
Okay.